Hello, I'm Clint Payne. Welcome to the fifth and final ME350 thermodynamics videos I'll be doing. Number 1 and 2 on learning assessment 5. A little crunch for time, as you can tell. I even put my hair up so I could save money on wiping my hair out of my face every 5 seconds. So assume the following, answer the following questions about humid air. Use these tables, assume air is an ideal gas, and use these volumes. So part A, what is relative humidity where water condenses? Well, I have an equation for that. Relative humidity is the partial pressure of water vapor of water over the saturated vapor pressure of water at the given temperature. Okay, so relative humidity is relative to the temperature, of course, and it's the amount of water stored into the air is what it's measuring. So say that your partial pressure of the water vapor was equal to the saturated vapor pressure, then your relative humidity would be equal to 100%. At this 100% is called a dew point. That's the where condensation occurs because at that point the air cannot hold any more water, so it must condense. Part B, how much mass of water vapor can air hold at 50 degrees Celsius? So we know that water vapor is a combination of water plus air. So we're going to be finding the specific volumes of both of these at 50 degrees Celsius. For water, it's as simple as looking at table A2, and we're going to grab the saturated vapor specific volume so we get the max amount of mass of water vapor. So that's going to be 12.032 meters cubed per kilogram. For air, it's a little more complicated because table A22 only gives you these relative values for specific volume. And we're given a specific volume, so we know that. So we're going to use that to solve for the specific volume of air at 50 degrees. These are STPs. And these will be 50 degrees Celsius. We're going to grab the VRs from the tables, table A22. I'll show you the interpolation process I used, because when we really think about it, isn't thermodynamics just a long series of interpolation processes? So our V relative is going to have no units. This is going to be in Kelvin. So convert our 50 degrees to Kelvin, you're going to have 323.15 Kelvin. Your ranges are going to be 325, 508.4, X, 320, and 528.6. All right, so VR1 is going to be equal to X. It will be equal to 515.87 without any units. So now we're going to look at the STP value. Standard temperature, that's 0 degrees Celsius. One more interpolation. So that's going to be 273.15 Kelvin. This is the same as before. We're going to be solving for the V relative. So use the ranges 280 and 270. You get 808.0 and 738. From the steam table A22. So VR2 is going to be equal to X, and it'll be equal to 75.95. All right, so now we're going to plug it into the formula to solve for a specific volume of air at 50 degrees Celsius. Plug in the given. Plug in the ratio of these two relatives. You should get a small value. And you should get 0.536. That's the air specific volume. So to get the density of the water vapor, we're going to do the inverse of these waters and airs specific volumes, because the units for a specific volume are the inverse of the units for density. So we just take the inverse, we can get a density value. All right, so density of water vapor at 50 degrees Celsius will be 0.0796 kilograms meters cubed. The problem does not state any kind of volume variable, so we're just going to plug in whatever we feel like to find the mass. So at 1 meters cubed times our density value, the mass of the water vapor can be 0.0796 kilogram at 50 degrees Celsius. Do the same thing for part C. Okay, so in part C, the air specific volume we'll use would just be the STP because 0.01 is barely different from 0 degrees Celsius. It's not a big enough difference to change the specific volume, that's for sure. So B air will be equal to BSTP, that will be equal to 0.816 meters cube kilogram. Yeah, my camera's still in range. All right. So now we're going to do the same thing we did in part B for water. And that's going to be at 0.01 degrees Celsius. Your VG for the max amount of mass would be 206.136 meters cubed per kilogram. Do the same as we did before to solve for density of water vapor. All right, so density of water vapor will be equal to 0.0048 kilogram. Ooh, close one. Meters cubed. I'm looking at the perfect. So at 0.01 degrees Celsius and pressure of 1 meters cubed, the air can hold a mass of, let me change this to a B. Move this down a little just so you can see better what I'm doing. It can hold about 0.0048 kilograms, just kilograms. Yeah. All right, so these density values are kind of supported by what I found on Google, where I searched up the density of water vapor, and they're around the numbers we find here. They vary a little bit because they may have used different assumptions than we did. I believe this one's 0.083 and this was 0.005. So that's the masses at these temperatures. Okay, part D, assuming the composition of your breath does not change, what is the reason why your breath could immediately condense at 20 degrees Celsius but not at 0.01 degrees Celsius? The Galactic kinetic assumption, so it's just saying that your air you're breathing out isn't turning into carbon dioxide. So the condensation of your breath is not just dependent on temperature, right? It's dependent on the relative humidity. So as we established in part A, at relative humidity is equal to 100%, you reach your moisture maximus, your dew point, and at that point, the air cannot store any more water, so it has to condensate, or condensation occurs. So since your relative humidity and your saturation pressure associated in the denominator is relative to the temperature, this can explain why on a hot and humid day at 50 degrees Celsius in Gainesville, Florida, you can sometimes see your breath condensate as you're breathing it. It's like you're a dragon, like, ah. At least that's what I thought when I was a kid. But whereas on a colder and dry day in the Siberian tundra at 0.01 degrees Celsius, if the air is not saturated enough, you will not see your breath. And the relationship between the lower temperatures, that kind of comes from the steam tables, where if you just look at the saturated pressures at the temperatures, they're generally much lower compared to higher temperatures like 50. And so the relationship is you can it generally takes less amount of pressure of your water vapor at lower temperatures to see condensation occur, but that won't always be the case because it depends on how moist the air is, and thus the relative humidity's role. And that's all for number one. Thank you.